Hello guys, welcome to DataFuse Analytics. In this chapter, we will look at transformers and how they work under the hood with all their components. The aim is to study all the building blocks of transformers in depth. We will also look at the architectural differences between encoder and decoder. I will try to explain the concepts in an intuitive manner by simplifying the logic behind them. Transformers is based on encoder-decoder architecture and is widely used for various tasks like machine translation, text classification, token classification, question answering, language modeling, language generation, multimodal classification, conversational AI, as well as in text representation generation systems. Transformers are extremely important because they can easily handle long-distance dependencies. The transformer contains two major components, namely an encoder and a decoder. The job of an encoder is to convert an input sequence of tokens into sequence of embedding vectors. This sequence of embedding vector are often called as hidden state or context vector. The aim of the decoder is to use this encoder hidden state or context vector to iteratively generate an output sequence of tokens, but one at a time. Now, let's look in the stepwise manner the flow of text from encoder to decoder. Initially, the input text is tokenized and converted to token embeddings. This token embeddings is then combined with positional embeddings. The aim of these positional embeddings is to inject the information of position of each token in the input text. This is done because the attention mechanism is unaware of the position of tokens in the input text. Then, this text passes via encoder stack or encoder layers. For now, we can view these layers or stack as that of stacking convolutional layers in computer vision or in CNN. This concept applies for the decoder stack as well. The encoder outputs something called as hidden state or context vector. The output of encoder is then passed to the decoder layer. Now this decoder layer is responsible to generate a prediction for the most likely occurring token in sequence. The output, which is generated by the decoder, is again fed to the same decoder until end of sequence or EOS is reached. In the coming slides, we will be looking into more details about this encoder and decoder mechanism along with mathematical equations behind them. But wait, there is a question, or there is an interesting question. Can we have only encoder or only decoder based architectures? Now, as discussed earlier, the transformer was originally meant to solve sequence to sequence or text to text based problems like machine translation, text summarization, etc. But as the time passed by, there is a tremendous research conducted where both the encoder and decoder architectures were used as standalone models. So the answer is yes. We can use only decoder or only encoder based architectures given the problem statement that which we want to solve. Encoder models output a rich representation of given input text in the form of hidden state or context vector. This type of architecture is more suitable for problems such as text classification, named entity recognition, etc. This representation computed for a particular token in a sentence encompasses both the right as well as the left context. To simplify this, the representation computed for a particular token contains the information about token occurring to the left and tokens occurring to the right of that token. This is also called as bidirectional attention mechanism. Popular models of encoder-only mechanism are BERT, Roberta, etc. Decoder-only models generate text given a prompt or initial starting tokens. These models will try to autocomplete the input prompt by predicting the most probable next token. GPT family is a popular models that fall in decoder-only architecture. The tokens generated in decoder-only architecture depends only on the left context. This is also called as autoregressive attention mechanism. The final type of architecture we have is encoder-decoder models. So these encoder-decoder models are used to learn the complex mapping from one sequence to another sequence. This type of architecture is widely used to solve tasks like machine translation, text summarization, etc. Now, let's look into the working of encoder in more details. A typical encoder has two important sublayers, namely multi-head self-attention layer and fully connected feed-forward layer that is applied to each input embedding. This figure depicts an architecture of an encoder. To understand an encoder, we have to learn about the encoder building blocks or components that make up an encoder. So there are 5 important components of encoder, namely self-attention, feed-forward layer, layer normalization, positional embeddings, and classification head. Now let's look into the attention mechanism and its importance, and let's understand why we actually need attention mechanism. This attention is a mechanism which allows neural networks to assign variable weight, or we call as attention, to each token in a sentence. The main aim of attention mechanism is to compute contextualized embeddings of each token in a sentence. Hence, attention mechanism is used to dynamically highlight important features of input text. Now we will see this visually later during implementation sessions. Now let's see this important procedure to compute self-attention mechanism. There are different ways with the help of which we can implement a self-attention mechanism, but the most popular technique is called as scaled dot product attention. Now this technique, which is called as scaled dot product attention, is introduced in the paper titled as Attention is All You Need. There are 4 major steps in computing a scaled dot product attention. Step 1 is we have to compute something called as attention scores. To compute attention scores, we have to project each token embeddings into 3 vectors. These 3 vectors are called as query, key and value. Q, K and V. So Q stands for query, K stands for key and V stands for value. In step 2, the aim is to determine how much the query and key vectors are related to each other, or how much the query and key vectors are associated with each other. For this, we require some kind of similarity measure. The similarity measure used is called as scaled dot product. Hence, the name of this technique is given as scale dot product attention. Queries and keys which are more similar or more related to each other, they have high dot product or high overlap. The output of this step, which we get after matrix multiplication, is called as attention scores. Now let's move to step 3. In step 3, we compute attention weights. The dot product or attention scores between query and value, which we computed in step 2, can produce arbitrary huge values. This destabilizes the entire training process. Now to solve this problem of instability, the attention scores are scaled to normalize their variance and then further normalize using a softmax so that column values are summed to 1. The output of this step is a matrix which is called as attention weights. In the final step, that is in step 4, we update the token embeddings, or we update the original token embeddings for a particular token. In this step, the value vector is multiplied with attention weights which we got as output from step 3 or from the previous step. In this way, we get an updated representation of each token in a sentence. So in this way, the entire self-attention mechanism works. Now you all might have wondered why we are using such terms like query, key and values. The intuition of query, key and value vector may seem a bit strange and confusing the first time you encounter them. These names are inspired from information retrieval or IR systems. Now let me try to explain this with a simple real life example. Imagine you want to cook pasta and you know the recipe to cook a best pasta. Hence, you go to a supermarket to fetch the ingredients to cook your pasta. These ingredients that you have on your mind can be called as queries. The labels associated with each item on the shelf of supermarket can be called as keys. Here you have to match your ingredient item with the items contained in the supermarket. Hence you have to check for query that matches with the key. To find this match we need some sort of similarity function. Remember the dot product which we computed in the last slide of self-attention mechanism? That is the similarity function here. In this way, you will get a key, that is item, for every query, that is for ingredient. You can smoothen the behavior by doing the following thing. If your list includes a macaroni, then you might end up getting penne or macaroni or spaghetti and ravioli. So this is the intuition behind using the terms like query, key and value. Now let's get into the next layer, which is called as feed-forward layer. The feed-forward layer in the encoder and decoder is just a simple two-layer fully connected neural network. The twist is that it processes each embedding independently instead of processing the whole sequence of embeddings as a single vector. Hence, it is also called as position-wise feed-forward layer. An important point to remember is that this layer is most often scaled when scaling models in production because it is assumed that most of the capacity and memorization happens here. The next component of encoder is layer normalization layer. The aim of layer normalization layer is to normalize each input in the batch to have zero mean and unity or one variance. When we implement layer normalization, we can adopt one of the following two categories, namely post-layer normalization and pre-layer normalization. Now let's look into brief about post-layer normalization. As you can see in this figure, in post-layer normalization, the layer normalization is between the skip connections. But this kind of arrangement is tricky to train and hence we use a concept which is called as learning rate warm-up. In this concept which is called as learning rate warm-up, the learning rate is gradually increased from small value to some large value during training time. The next type of normalization is pre-layer normalization, as you can see in this figure, where the normalization is placed within the span of skip connections. This kind of arrangement is most common during implementation because it is more stable during training. This also does not need any kind of learning rate warm-up. The next component of encoder is positional embeddings. The main idea behind this positional embeddings is to augment the token embeddings with position-dependent values patterns in a vector form. These positional patterns helps the attention layer and feed-forward layer to learn the positional information of each token within a sentence. Now, there are two kinds of positional embeddings. The first type is absolute positional representation. In this type of representation, they use modulated sine and cosine signals to encode the position of the tokens. This is the static type of representation and this works well when the volume of data is very huge. The next kind of token embeddings is called as relative position embeddings or relative positional representations. The absolute embeddings are no doubt important, but we know that when we compute an embedding, the surrounding information in a sentence is important or vital to provide necessary contextual meaning, and hence we use relative positional representations. Relative positional representations helps to compute the contextual meaning by encoding the relative positions between tokens. This is achieved by modifying the attention mechanism itself by introducing a few additional terms or parameter. Models like DBERTA use these relative positional embeddings. The final component is called as classification head. Transformer models typically consist of task independent body and a task specific head. Now let's assume we need to develop a text classifier. For an example, we want to develop a text classifier which classifies sentiments into positive sentiment or a negative sentiment. We need to attach classification head to the body of transformer. You all know that we have prediction for each token in a sentence, but we want only one prediction for a certain token. Here, most commonly, the prediction is often made using the initial token, and we can add a dropout and a linear layer to generalize a classification prediction. Now that we have learnt encoder and all its components, let's understand the decoder and what exactly is the difference between an encoder and a decoder. As you can see here in this decoder architecture diagram, we can observe that the architecture is similar to that of encoder with only one major difference. Decoder has two attention sublayers instead of one attention layer, which we saw during encoder. These attention sublayers are called as masked multi-head self-attention layer and encoder-decoder attention layer. The decoder mainly deals with text generation, and the main idea here is that the tokens which are getting generated at each time step are only dependent on the past generated tokens and current token being generated. It should not have any information about future tokens. Hence, we use masked multi-head self-attention layer. That is why masking is used here, so that it should not look in the future tokens. It should look only at the current token being generated and the previous tokens. Without this layer, the decoder could cheat during training by simply copying the target translations. The encoder-decoder attention layer performs multi-head attention over the output key and value vectors of the encoder stack. Here, the queries of the intermediate representations of the decoder. In this way, the decoder learns how to map input sequence to output sequence. For an example, translation from one language to another language. A point to note here is that the decoder has access to encoder keys and values in each block. So that's it, guys, with understanding of encoder and decoder mechanism in transformers. Thank you for watching this video. Please like, share, comment this video and subscribe to the channel DataFuse Analytics. Thank you.